We present modal folding, an automated method for discovering folding patterns using strain space modes. Folding transformations are used in many aspects of daily life, including arts and crafts, interior design, architecture, and engineering. However, discovering folding patterns is a challenging problem and computational tools are scarce. In this work, we present modal folding, a novel approach for automatically discovering folding patterns of sheet materials. Folding transformations generally correspond to large deformations that require little mechanical work. Using this principle, we cast the discovery of folding motions as an optimization problem where we seek to find configurations that minimize internal energy for prescribed deformation magnitudes. For linear materials and small deformations, solutions to this problem correspond to the well-known elastic eigenmodes. Indeed, linear modes indicate promising directions that prefer bending over stretching. However, they are inherently unable to capture the rotational motion required for folding. To address this limitation, we introduce strain space modes as nonlinear analogues of elastic eigenmodes transformed from Euclidean to differential coordinates. Our key observation is that linear trajectories in strain space can give rise to complex nonlinear motion in position space. We leverage this insight to build a simple and effective modal folding method that tracks strain space transformed eigenmodes in a physics-based and material-aware way. Strain space modes have several important advantages compared to existing alternatives. For example, whereas the nonlinear compliant modes by Dunzer et al. Generate bending initially, their reliance on external forcing with constant direction means that sheets must ultimately stretch. We furthermore experimented with another nonlinear extension of eigenmodes, the rotation strain modes by Huang et al. The lowest order rotation strain mode initially shows a small in-plane deformation. However, it clearly exhibits double curvature, which translates into non-zero in-plane deformation. As a second basic example, we compare the 4 different mode types on a simple origami design. As can be seen here, only our method successfully reproduces the twisting behavior. Strain space modes can generate diverse and interesting folding transformations for a large variety of input shapes and materials. We first apply strain space modes for a square sheet. In order to help the fabrication of such folds, we develop an interactive tool for selecting pairs of vertices and incorporating them into the static solver using soft springs. After getting the solution from the static solver, we can preview the result and compare it to the result without gluing. We can repeat this procedure until we achieve the desired shape. As can be seen from the results, the physical prototypes reproduce all these non-trivial folds in the simulation. Periodicity plays a central role in many folding patterns, offering both aesthetic appeal and functional advantages. With translation tiling, we obtain several interesting periodic patterns from a square sheet. We further explore the modal folding under the reflection tiling. Here we show the results of a square sheet under reflection boundary conditions with their corresponding physical prototypes by copper sheets. It can be seen from the results, our fabricated physical prototypes successfully reproduce these complex folding patterns. We apply our method to a disk sheet as shown here. Even with a simple input structure, our strain space modes facilitate the discovery of diverse and aesthetically pleasing folds. We further demonstrate our strain space mode to a more complex pattern. In this example, we employ a thin sheet with the shape of a live flower pattern. Our method proves effective in exploring the folding patterns of this complex shape. In addition, it can be seen from the results that our fabricated counterparts can closely track the results obtained from the simulation. We consider an inverse folding problem where the goal is to find a folding transformation for a fabric disk such that it fits into a sphere. As can be seen from the result, inverse design with strained space modes leads to a smooth and three-fold symmetric folding pattern. The contact-driven variant, in contrast, appears crumpled rather than folded. Thank you.